Okay, Assalamualaikum and good afternoon. So we continue our lecture on the tutorial for Von-Karman equation. So previously we learned about how to derive Von-Karman equation. So I hope you remember tau is equal to rho u square d theta dx. So and then we could calculate also, we know the shear stress also can be calculated by using the Newton's viscosity of law. So which is mu du dx k at y equal to 0. So I hope these two equation you could remember this equation. So let's say question number 1, determine the boundary layer thickness and drag coefficient in laminar boundary layer that have second order polynomial velocity profile. So this is the question for final exam.
Oi, Boka.
So this is the equation for one of your final exam, one of the previous final exam. So they ask you to calculate, to determine the boundary layer thickness. So now the question is to calculate what is the value of delta, and at the same time you need to calculate what is the value of CD, coefficient of drag, okay, and it gives you the idea of second order polynomial velocity profile. So here, the second order polynomial velocity profile, I already answered that in previous tutorial. So I hope you could check that one. And in this question, you need to start from that one. So I mean, you need to start with the normal, the general velocity profile. You mean A plus BY plus CY square. And then you need to start with the boundary condition and so on and so forth. Okay, because the question asks you to prove the second order polynomial profile here. Okay, but for this tutorial, I skipped that one, okay, because it is just to, we want to focus on how Von-Karman equation being used. Okay, so let's say you managed to get your second order polynomial and the answer is like this. So u over u 2y over delta minus y over delta square. And then you list down these two main equation. So the shear stress is rho u square d theta dx. So this is the Von-Karman and this is the Newton's law of viscosity. So you have tau rho u square d theta dx and also tau mu du dy at y equal to 0. Okay, please remember the condition which is y equal to 0. So and then, so we need to solve Von-Karman equation. We need to solve this equation. So from this equation, the unknown is d theta. So what we need to do is we need to calculate what is the value of d of theta for this velocity profile. So means that this is the equation. This is the equation for theta. We substitute u over u here with the velocity profile. So in this question, we use second order polynomial. If the question give you velocity profile with power of 4, so and then you need substitute here with the given velocity profile. Okay, so and then everybody know how to do this, so I skip the solution. So we know that the theta for the second order polynomial here, it is equal to 2 over 15 delta. Okay. So and then how we want to use the Von-Karman equation? Okay, please listen to this. Okay, so this is the equation of Von-Karman. Tau equal rho u square d theta dx. Okay, so this style of writing maybe confuse you a little bit. So it is okay for you to change the way they write the equation here into this kind of equation. So means you have run now tau rho u square d over dx for theta. And then what you need to do is you substitute the value of theta here. So it is 2 over 15 delta. So and then, okay, so and then we solve the problem for shear stress by using Newton's law of viscosity. So this is the equation. Tau is equal to mu du dy at y equal to 0. So I hope you understand. We need to solve this first. So means that this is the u over u. And then we bring the u from the left side to the right hand side here. So we have 2u y over delta minus u y over delta square. And then we differentiate it du dy. And finally we could have 2u over delta minus 2uy over delta square. So and then please do not forget to insert the value of y equal to 0. So if we substitute the value of y equal to 0 means the 0 is here. So the value is 2u over delta. So we need to write again, tau is equal mu du dy at y equal to 0. We substitute the value of du dy at y equal to 0, which is equal to this one. And then finally, we could get the value of tau here is equal to mu 2u over delta. Normally, students forget to substitute to do calculation for this stage. Means student simply says that tau is equal to u over delta. So this is totally wrong. Okay, so I hope you please do not make any simple mistake here because it will ruin your all marks. Okay, now you already calculate, you already solve two equation for shear stress. One is von Karman, and another one is Newton's law. So next, what you need to do is, because both of that equation is expressing the shear stress, so what we need to do is we equalize that both equation. So we equalize the von Karman with the Newton law. So this is the von Karman. So we have rho u square d dx 2 over 15 delta, and this is the Newton's law. We have mu 2u over delta. So we need to solve it because please remember the question. So the question asks us to calculate what is the boundary layer thickness. And boundary layer thickness from this equation can be represented as delta. So means that our aim now is to calculate what is the equation of delta. Okay. So, okay, let's say we bring this 2 over 15 out from this bracket. So we have this one, 2 over 15 rho u squared d delta dx and mu 2u over delta. And then, as I said, we are aiming to get the equation for delta. So what we need to do is we bring all the delta terms to the right-hand side. So we have d delta here, and also we have delta. So we bring delta to the right hand side here, and then we bring all of this term to the left hand side here. So what we have now is something like this. So and then you could simplify it. So it's the left hand side is remain d delta, and the right hand side will become 15 mu over rho u times dx. Okay. So and then what you need to do is, okay, the delta d delta here is still not a complete equation. You know, equation should not have any dx, dy, and so on and so forth. It's still in terms of differential terms. So we need to erase, we need to eliminate the dx, the d delta and dx here. but you cannot eliminate it just like that. What we need to do is we need to integrate all these both terms. So you already know to do this, I think. So let's say we integrate both of these equations. So we have the integral delta d delta and integral of 15 mu rho u dx. So integration of delta d delta will give us delta square over 2, and the integration of 15 mu will give us 15 mu x over rho u plus c. So and then please do not forget to add this constant. So and then we need to check whether the value of c is exists or it's 0. So we just substitute this boundary condition. So let's say at x equal to 0, so means that if we have a plate here, so this is the wind comes in. So this is the x equal to 0, the starting point. So and then at x equal to 0, the boundary layer thickness is still not exist. So if we substitute the x is 0, the delta is 0, then the value of c will become 0. So finally, if you prove that the value of c is equal to 0, now you could write your new equation like this. So you have d square over 2 equal 15 mu x over rho u. So and then I hope you understand we are aiming to have equation for delta. So what we could do is we could simplify this term. Okay, so you just rearrange it, and finally you will get the delta is equal to 5.48x over square root of Reynolds number. Okay, so here, if you do this at home, you will find that at the same time, okay, after you substitute everything and you rearrange everything from left to right and so on, you will get only this term, 30 mu x over rho u. So it seems that there are no Reynolds number there. Okay. What you can do here is, you know that Reynolds number is rho u x over mu. But what you could see here, you have rho u and x here. You have rho, okay, let's say you have rho u and mu here. So you don't have this term x. So what you could do is you could multiply both of them with x over x. Because x over x here is equal to 1. So mean you multiply that terms with 1. So it's not change the amount. It's not change the value. It's just the tricks for mathematics. So now, after you multiply it with x over x here, you could see that you have term rho u x over mu here, and then you could replace it like this. And finally, you could simplify rho u x, mu over rho u x here can be simplified as Reynolds number. So, and then we have square root here, square root the left-hand side, and also we need to square root the right-hand side. So you could get 5.48x over square root Reynolds number. Okay, so why we need to make sure that our final answer has Reynolds number, because this is the universal terms. You could open many textbooks, they will give you answer in term of Reynolds number. So this is an official term. So if you say that delta is equal to square root 30 mu x over rho u, okay, actually your answer is correct, but okay, you still did not get your final marks, because this is the final answer. So please make sure that you could prove your answer into Reynolds number. Okay, so and then this Reynolds number at this answer is actually only for second order polynomial, mean only for given velocity distribution. If your velocity distribution change from second order to sinusoidal, so the value of 5.48x is not valid anymore. You need to do this calculation again, and then you need to determine your own your new value of delta. So means, please do this at home for all the velocity profile. So please refer back to my previous lecture. We have 6 velocity profile. So please try all of them and try to get what is the value of delta for each velocity profile. So, and then I would like to show you how to use this delta. Okay, for example, so let's say we have a flat plate here. Okay, flat plate. So, and then you have a wind blow from left to right here, and then it will create boundary layer. So, and then, so for example, we have a 2 location. One is x1 here, and another is x2 here. Okay, so you could calculate, means you could estimate what is the distance, what is the boundary layer delta 1 here, and also the boundary layer thickness here, delta 2. Okay, how to use that? It's very simple. So you just substitute the value x here with the distance. So what is the distance here? Let's say this is 0.75 meter. So you just substitute the x with 0.75 meters, and then you need to substitute the value of Reynolds number at the same location. So we know that Reynolds number is rho ux over mu. Okay, so you substitute the x here with 0.75 meter. So you substitute the value of u, means the value of u here. Okay, the value of uniform flow. You need to substitute the density of the fluid. If the fluid is air, you need to substitute the density of air. If the fluid is water, you need to substitute with the density of water. And then this is the dynamic viscosity. So you need to substitute the dynamic viscosity for the fluid. Okay, if the fluid is water, so you need to substitute with the dynamic viscosity of fluid. Then you get this Reynolds number, you substitute it here, then you could calculate the value of delta. So means that if you use information for x1 here, you will get the boundary layer thickness at point 1. If you use the information at point 2 here, so you will get the delta at point 2. Okay, this is the idea how to use the von Karman equation, and it will lead you to boundary layer thickness. Okay, so this is the example. As I said, for example, we have let's say we have a point 1 here. So the information is the x is 0.4 meter and the rho is 1000 kilogram per meter cube. So the fluid is water. So this is the kinematic viscosity for water, and let's say the water flows at 0.2 meter per second. So we could calculate the delta by substituting the value of x here, and then we could substituting the value of Reynolds number here, and then we could found that the delta is equal to 7.75 times 10 by the power of minus 3 meter. Okay, please understand that delta here, the boundary layer thickness, is thickness, ketebalan. So means that the unit should be in length. You learned about dimensional analysis previously. So okay, so it must be in length, whether it is meter, centimeter, millimeter, or so on. Okay. So, and then we need to calculate the drag force. Okay, so we need to start with shear stress. Okay, if you still remember, at the beginning of this calculation, we have two equations telling you about the shear stress. One is from von Karman, this is from von Karman, and this is from Newton law of viscosity. Okay, in this next calculation, you need to use the shear stress from the Newton law of viscosity here, because in von Karman equation, okay, the equation is not ready yet. If you see the equation here, it still has the terms in differential terms. It still has d theta over dx. So means that the equation is still not completed. Not so it still have d theta dx. Okay, so please do not use shear stress equation from von Karman. Use shear stress equation from Newton here because the equation is complete. So what we do is, we know that theta is tau here is equal mu 2u over delta, and then we substitute the value of delta here with what we have previously. So, and then we could get this term. So you just substitute everything. So we have 2 here. So, and then you solve it, you could get it is 0.365 mu u over x square root naught. So, and then, okay, so we have, if you have a plate like this, okay, so this is the velocity profile, and then we have two types of drag coefficient. One is called local drag coefficient. So the symbol is C with a small d here. And the total drag coefficient, so the total drag coefficient is written as C with capital D, like this. Okay. What is the local drag coefficient and what is drag coefficient? So local drag coefficient here, okay, the local drag coefficient here is actually, it only refers to one single point. So it refers to one single point on the plate. So for example, so we are focusing on this point. So at this point, it will have CD. So it's focused on one single point. So that's why we call it as local drag point. Local here means at very specific, at very one specific point. So, and then what is the meaning of drag coefficient here? So drag coefficient here, it refers to the total drag coefficient from the beginning until the end of this plate. So means the drag coefficient here is the total one, the overall one, the total or overall. Okay. So I hope you could understand the difference between local drag coefficient, CD, and the drag coefficient. So this is very important because the equation is not the same. Okay, we focus on local drag coefficient first. So the local drag coefficient, okay, we know that the tau is equal 0.356 mu u over x Reynolds number. So we get this from the Newton's law of viscosity. So, and then this is the equation that you need to remember. Okay, so according to the experimental, and then we compare with the theoretical and so on, we could conclude that shear stress, okay, can be calculated by this equation. So tau is equal CD 1 over 2 rho u square. So this is actually comes from the idea, for the basic idea, we know that drag force, okay, drag force is equal to C capital D 1 over 2 rho u square A. So, and then the relation between shear stress and a force is actually tau times A. Okay, so and then we could cancel off the value of A here. Now it will become tau equals CD 1 over 2 rho U square. But the value of CD here is actually cannot be used straightforward. So it need to be changed as C small d 1 over 2 rho U square here. Okay, because the value of drag coefficient and local drag coefficient is totally different. That's why we need to change. So this occur when you do experimental work. You could see the different means you need to change the coefficient. So this is the idea from we comes out here. The tau is equal C small d 1 over 2 rho U square. So you could see here we have two equations telling us the value of shear stress. So and then if you equalize both of these equations, you could say that CD is equal to 0.73 over Reynolds number. So I hope you could try this at home. So the calculation is simple. I just give you the idea. Now we go for the drag force. Okay, drag force. So as I said in my first lecture, we have two types of forces. One is lift force and one is drag force. And drag force is the total forces that occur on x-axis. So that's why we could say that the force here is integral of 0 to L tau b dx. Okay, so it is come from the idea of this one. Okay, let's say we have a plate here. So we have a lot of molecule on it. So each molecule will give shear stress. So means that the total shear stress on this surface, okay, can be calculated by the idea of tau A. Okay, so means that, okay, however, okay, the value of shear stress here is actually cannot be calculated in terms of linear. So we need to do integration. So if we write them into the integration equation, we could say that, okay, let's say we have a small area here. So, okay, this is the 3D shape of this plate. Okay, for this small one, so let's say we have a df here. So it is equal to tau dA. Okay, this is a small dA here, mean a small area on the flat surface. So, and then dA here can be written as B, mean the width. Okay, this is the width of the plate. So, and then we multiple with dx. So dx mean the small distance on x direction. So this is dx. So and then to get the total force, so we integral these both sides, left and right. So and then the integral of F will become total drag force. And then the integral of this one is shown like this. So integration of tau b dx. And every integration must have limits. So the limit is 0 to L. So 0 is here. And at the end here, so we denote as L. So L is for length. So means that 0 to L will show the total length of the flat plate. So we substitute the value of shear stress that we get from the previous calculation. So we have here the value of shear stress. So we substitute into the equation and then we solve the equation. Okay, so because we are integrating this one to dx, so means we need to expand the Reynolds number here. So we expand the Reynolds number, so we have rho ux over mu. So and then you could simplify with this term and so on and so forth. So you may have this kind of equation. So please try this at home. Okay, so and then, so this is very straightforward. So we have x here. So we need to integrate this into dx. So actually you are doing integration of this x by the power of -1/2 only, because another term is not related with dx. So if you do this, you will get this one, x by the power of 2 square root x with 2 here. So that's why you will have 0.365 multiplied times 2. You will get 0.73. So and then you substitute the limit 0 to L. So you will get this one. Okay, so and then you could have this value. So this is the drag force that occur on that situation. So now you could substitute the value of width, the value of total length, and then you could calculate the total drag force that occur according to the boundary layer. And then we could calculate the drag coefficient. So how to calculate the drag coefficient? So the idea is simple. So we know that this equation is valid. So means that I already tell you about this equation. Now we need to calculate what is CD. So we rearrange the equation. So we have this term. And then we know that the A here is L times B. So and then we could substitute the value here. So we substitute the value of drag force that we get previously into this equation. So and then if you simplify that equation, finally you will get the CD is equal to 1.46 over square root Reynolds number. So this is the drag coefficient for velocity profile, second order velocity profile. So please do not make mistake. Okay, this CD is not for all conditions. So this CD is calculated based on the specific velocity profile. So in this question, we use second order polynomial, mean velocity profile with by the power of 2. So you will get its specific delta and also the specific value for drag coefficient. So and then I hope you could do this again at home, and please make sure that you could get this one. So if you do the u over u equal y over delta, so you could get the value of delta like this. This is the value of CD, and this is the value of drag coefficient. So this is what we do right now. So second order polynomial, parabolic. So we could have this one. And then if you do by the power of 3, so you will get this one. So if you do with the by the power of 4 here, so you will get all of this value. And if you do the sinusoidal, you will get this value. So next lecture, we will focus on Blasius exact solution. So what is Blasius exact solution? So we will go for the next chapter.